Great. So next, I would like to introduce Gleb Oshanin from the Université Pierre et Marie Curie. His research interests lie in condensed matter theory, non-equilibrium and equilibrium statistical mechanics, chemical physics, and many more.
Thank you. Thank you very much. And also, I would like to thank the organizers for this beautiful occasion and the workshop, which enlarges largely scopes. So giving a possibility to meet people interested in statistical mechanics, stochastic processes, and in general, various learning algorithms. So thank you very much. So just some small rectification. It's no longer Pierre Marie Curie University. From something like 5 years or 6 years, we're already Sorbonne, which significantly helped to go up in Shanghai index. And in general, we're making the future, as you can see from the logo here, already for something like 800 years, we are working on our better future. So today I will talk about some recent result of ours on spectral densities. So the full title is Spectral Density of an Individual Trajectory of an Arbitrary Gaussian Process. So Gaussian stochastic process does not contain any ambiguity, it is clear. Individual trajectory, it's also clear, but here is some ambiguity, because usually in standard definitions and in textbooks, spectral density or power spectral density is understood as something which is specific to enhanceable. It is enhanceable average property. And I will talk today looking on this property from a broader perspective. I will define spectral density of an individual trajectory, so it will be a random variable, or better to say random functional, parameterized by observation time and frequency. And I will show that actually for Gaussian stochastic processes, you can tell really a lot. You can determine for arbitrary Gaussian processes some inequalities of the noise to signal ratios, and moreover to derive full probability density functions of such random variables. So let's go back to the textbook definition. And we suppose that we have some arbitrary real value stochastic process or signal, xt, and t is a continuous variable. For example, it is time. It is very clear for experimentalists who look on something which moves in a system and they record positions of the particle. It can be understood as a trajectory. But in more general things, it can be some signal or noise or whatsoever in engineering systems or in applied mathematical systems. And then standard power spectral density is defined in the following way. It is some functional, I will tell you a little bit later. This stands for an average over available statistical sample. And then you take a limit of an infinite observation time. And here, SFT, it is something which is defined on a level of a single trajectory. So it is finite size to Fourier transform of the trajectory. F stands for the frequency, T for the observation time. This is an imaginary unit. You take absolute value, square it, and that's it. So this is the real value to think, as I will talk, concentrate exclusively on this case here. Then you simply can develop it, and you get the following thing. So this is the position at time t1, this is position at time t2 of this individual trajectory, and this is weighted by cosine with frequency and the difference of time, and you integrate twice. Now, also what is interesting here that if you set exactly frequency equal to 0, then this property takes a much simpler form, of course, and you understand that it is simply a squared integral under a random curve. And this is typically an increasing function of time of the observation time, because you accumulate more and more fluctuation. It is a fluctuating property, and so on and so forth. But as it stands, this property, standard textbook property, is entirely defined by the covariance function of the process xt. That's it. And evident question, of course, immediate question is that there are some awkward points in this definition. First thing, it is that going to infinite limit is not a good thing. First of all, of course, any sets of data are principally finite. All experimentalists live for a limited, have a limited lifespan. Also, if you do numerics and deal with numerical sets of data, they are finite. But also from mathematical point of view, it imposes very severe restrictions because the integrals don't exist most often. They require stationarity of the process xt, but they don't work. It is just infinity in the limit t goes to infinity. So it is something absolutely meaningful. And there is some line of thought how to avoid it. For instance, people use a little bit different definition like Wigner-Wille definition, but it is not very suitable, say, for experiment because of the limit to minus infinity, you have to impose somehow the history in the past, infinite past. But it's also a nice way of dealing for some applications. Modulo this constraint. And second thing, it is maybe even more severe because it is just first moment of some random variable, the standard definition. And we know when we have quite a lot of systems in which first moment doesn't tell you basically nothing because it is it occurs very often that this mean is associated more with the tail of the distribution. And as it is, it means that it is supported by some rare realizations. And if you have a small statistical sample, you don't see it. And for small statistical sample, it is better to talk about typical behavior. And this is precisely my motivation in this analysis. So the talk will be outlined as follows. I will start with an example which has been already mentioned here at several occasions. It is fractional Brownian motion. I will talk about what we get as a standard result or textbook result for fractional Brownian motion and go a little beyond, concentrating on the noise to signal ratio gamma. It will be called like this throughout my talk. And the gamma here will be noise to signal ratio, coefficient of variation of the distribution, which is standard deviation over the first model. Standard deviation is square root of the variance of random variable s. And then I will present some general view.
So mu is the first moment?
Mu is the first moment, and it will be everywhere denoted like mu. And then I will talk about actually general results, which will hold for arbitrary Gaussian processes. First will be, I will impose some, derive some rigorous lower and upper bounds on the noise to signal ratio for arbitrary Gaussian processes. Then I will present you the full probability density function, discuss typical behavior of S for small statistical samples, and eventually turn some very unusual behavior of frequency correlations of this realization-dependent random function S. These are two works with my colleagues in which these results have been presented 1 year ago. So let me recall you what is this object like fractional Brownian motion. It is a Gaussian process, and as such, it is entirely defined by the first moment and covariance function. First moment is usually taken equal to 0, so nothing pushes the walker to go either right or left, so there is no regular bias. And the covariance function is the following combination. So you see, and this H has been already quoted yesterday and today, it is the so-called Hust index. So at equal times, you get the second moment, which goes like t in power to h, and you see that h, which is bounded away from 0 and 1, it is so such that this behavior can be either super diffusive diffusive for h equal to 1/2 or subdiffusive. And actually it happens because we have except for the case h equal to 1/2, when we recover standard result for the Brownian motion, we have correlated increments. In the case when h is bigger than 1/2, we have positively correlated increments, which means that in the history I made steps in the positive direction. It will be most likely that on the next step, I will keep on going to the positive direction. And conversely, for the h less than 1/2, the increments are anti-correlated, which means that if I made this step to the right on the previous step, it will be most likely that I will turn back. And of course, because of that, I have a localized motion. So now I will show you that already on the level of standard first moment, the behavior can be quite different. We look first on the case when h is less than 1/2, but bounded away from 0. In this case, for t sufficiently large and f bigger than 0, we have the following behavior. So the leading term is independent of the observation time, and it goes like frequency in power to h plus 1. So the power is dependent on the dynamical exponent h. And in the limit t goes to infinity, we have the second term vanishes as such that we have a limiting form in this. For Brownian motion, the well-known result is here. The exponent here is 2, and it coincides with the fraction of the dimension of the trajectories of Brownian motion. In the limit t goes to infinity, this term vanishes, and just this is the amplitude which remains here. And it is believed and quoted in the literature almost everywhere that these two, it is a free fingerprint of Brownian motion. Now we come to the most interesting case of superdiffusive motion. And we construct series large time theories which look the following. Now the leading behavior in the large t limit is as follows. We again have 1 over frequency in power 2. And it is deceptive, it is cheating, which will mean that if we have sets of superdiffusive behavior and we calculate the spectrum of it using MATLAB and pushing the button, because typically spectral densities are built-in packages. They are very, very widely used. And it will be deceptive because if we work with a fixed time, we will make erroneous conclusion that we deal with Brownian motion. It is not the case. You have to look on the time, observation time dependence, on aging properties of the spectra, just to understand that you don't deal with Brownian motion. Okay. Now we go a little one step above the standard picture, and we look on the noise to signal ratio, so standard deviation over the first moment. We realize first that it is a function of omega, which is a product of frequency times observation time only. It does not depend on any parameters. Here on the plot, we have 3 groups of data. So dots are just the result of numerical simulations. Wavy lines are just full solutions. We have formulas which are very long, and solid lines are asymptotical curves, which you can also establish. And you see that actually all curves start from square root of 2 for either frequency 0 or time 0, and then they become completely different. This group above, it is what we have for superdiffusive Brownian motion, fractional Brownian motion. So for Hoost index 2/3, then 3/4, and 7/8. Then this singular case, it is a Brownian motion. And the curves above are subdiffusive fractional Brownian motions, which correspond to 1/3 and 1/4 for the Hoost index. And this already, when you look on it, it's quite strange because you see superdiffusive behavior is drastically asymptotic superdiffusive behavior as a function of omega is drastically different. So the case for superdiffusion, they go up to square root of 2. For subdiffusive case, when they go down to unity. And for Brownian motion, they go to a very particular number, which is square root of 5/2. And what is interesting about it, that h can be very close to 1/2, but not strictly equal. And it's enough already to have a very different behavior. And why it is important? Because actually gamma can serve a robust criterion of anomalous diffusion. It happens quite often, at least for me, who is referring some papers done by experimentalists who claim that they observe anomalous diffusion. So they look on mean square displacement. They say that it goes like t in power alpha, and alpha is 0.95. And you don't know if it is anomalous, so your fitting is simply wrong here. But this thing will tell you if it is indeed anomalous diffusion or diffusion. So, just we were actually quite aware of this possibility. So we, in 2 papers in which we are treating, proposing this gamma as a criterion of anomalous diffusion, we collaborated with several experimental groups of Matthias Weiss, for instance, from Erlangen and Bayreuth, Diego Krapf in Colorado, Zellhuber Unkel, Christine from Heidelberg, and also with the group of Felix Ritter from Barcelona. And actually, we produced a validation of our theoretical prediction on real stuff experiments. So let me pass to the main results. So I recall the definition of gamma. So it is a standard deviation over the first moment. So it is second moment minus the first moment. This is standard deviation here, square root of 8. And this is the first moment. And first result is theorem number 1, which states that for any frequency, any value of the observation time, any Gaussian process, gamma obeys a crucial double-sided inequality, 1 and square root of 2. Let me just show you an idea, some argument, a flavor of arguments giving you the idea how it can be derived in general. So you simply write the second moment, which enters here. It will be 4-fold integral, which includes the 4 time points correlation functions. Then, once we talk about Gaussian processes, we take advantage of Wick's probability theorem, which tells you that the 4-point correlation function decouples into all possible pairs of 2-point correlation functions. And that's it. This is the only point we need. Then you write the second moment in explicit form, where here you have introduced the notation for the following integrals, where you integrate covariance function over cos and cos, sin, sin, cos, sin, sin, cos, and you have different indexes here. And then you get that the variance actually is the following combination. First thing we want to prove it is that gamma, the noise to signal ratio, always exceeds 1. And this is very simple. You just add to this expression and subtract the following term. And then you see that you can rewrite it as a combination of full squares. This condition is tantamount to saying that the variance is bigger than squared first moment. And then you see that first moment is here, but this term is always positive. So it's automatically. But despite the simplicity, and I would say almost triviality of the derivation, it has a very important physical meaning. It tells you that standard deviation or fluctuations around the mean are always bigger than the value itself. And so the standard textbook power spectral density, at least for Gaussian process, is a bad property. Okay, the analysis of the upper bound is slightly more involved. So gamma less than square root of 2, it is the same as we say that variance is less than twice squared first moment. You do the same trick, you add and subtract twice the term which we added before, and we end up in this line with the following constraint. So we have to show that variance is always less than this thing, which is tantamount to saying that this should be negative. Or explicitly it is like this, or using the definitions of SCS and SCC and so on, explicitly we have to prove the following inequality. So we have the integral over cos times the twofold integral over sine, and we have to show that for any frequency and time, and actually any Gaussian process with the covariance here is bigger than the cross term like this. And it seems to be a hopeless task. But it is not the case. And let me recall you Mercer theorem, which states that if you have a symmetric function of two variables, which is defined on an interval OT, this theorem asserts that there exists an orthonormal basis, EK, of functions which are orthogonal on this interval, with positive set of eigenvalues lambda k, such that your covariance function admits the following representation, factorized representation. Everything is positive, everything is fine. And so let us define two auxiliary functions, sk and ck, just cosine transform of this orthonormal function and sine transform, plug it in back here, and we end up with the following thing, that this strange inequality with fourfold integrals and so on just becomes the following thing. And this is Cauchy-Schwarz inequality. So it holds. And for us, it is good because it proves the upper bound. Now, theorem number 2. So again, for arbitrary centered zero mean Gaussian process, like Brownian motion, fractional Brownian motion, Ornstein-Uhlenbeck process, Gaussian signals, any processes generated by fractional Gaussian noise, and so on and so forth, for any frequency and any observation time, the probability density function of random variable S is the Bessel function distribution. It is a monotonously decreasing function with a maximum at 0, so most probable value of single trajectory spectral density is 0, and then it decreases exponentially with such a tail, where gamma is gamma, what we defined, and this is mu, which is first moment. So, because we talk about Gaussian processes, it appears that spectral density of Gaussian processes, the probability density function, is also defined by first two moments. And you may understand why we needed actually the crucial inequality obeyed by gamma. Gamma has to be bigger than 1, gamma has to be less than square root of 2.
Surprising that the spectral density is also defined by the first two moments. Like to me, since I mean,
I wouldn't say it is surprising. I would not say it is surprising. And I will show you why, actually. It is not surprising.
I thought this was like the way one defines it. Then it would follow immediately that it's also the spectral density is also.
Okay. And so how to derive this result? And it is pretty straightforward. You start, because S is evidently positive definite, yeah, you use Laplace transform. So you calculate exponential of minus kappa, this variable. So explicitly like this. At the next step, you expand the cosine, like cos minus plus sine. So you see that it is in the positive density, and it is the sum of two squares. And then the crucial thing, which highly simplifies our life, is to resort to Karn and Loewe decomposition, which tells you that for any square interval Gaussian stochastic process xt with t defined on the interval OT, you have the following representation, where ek are the function from Mercer theorem, and zk are independent Gaussian random variables with the variance equal to lambda k. Again, back to Mercer theorem. You plug it to the definition of S. You get that now S is given you by two squares of infinite series. And then you make a usual trick. You want to get rid of squared variable in the exponential by first power of this variable. Then you get twofold Gaussian integrals here. You perform averaging over now independent variables here. And you end up at having the exact result that the characteristic function is 1 over square root of a polynomial of second order in kappa. And here we have some evidently positive term, and here we know that this is positive and everything exists and is legitimate just because of the theorem number 1. You identify next the coefficients here to realize that this infinite sum is just first moment. And this thing, we know what is it as well, and we realize that it is twice second moment minus the variance. So then you invert and get what you get.
So are you changing the order of integration summation?
No. I just perform infinitely fold integrals, Gaussian integrals. So it's not a big deal. Yeah. Now, typical value. What we know that actually, if we deal with small samples and we don't want to get rid to filter out some large deviations or some rare realizations, we rather talk about average logarithm. And so I define typical power spectral density, which will show us typical behavior, as an exponential of the average first logarithm. With the distribution which I have just presented, you can perform all integrals. And this typical will go like this. It is indeed proportional to the first moment, which contains most of the dependence on f and t. But you have an amplitude, which is exponential minus Euler-Mascheroni probability. So it makes up, and you have a little bit different behavior on the tail because also frequency dependence comes from gamma here.
So if you put the approximate form of gamma with the reverse index for Gaussian Gaussian process, do you get like for h larger than 1 or like 1 over 2, there will be like high frequency variable and what else?
It will, as we know that for high frequencies, it goes square gamma goes to 2, so it disappears and you get 1/2. For subdiffusive processes, so it goes to 1, so this whole thing goes to 1.
And for the super diffusive one?
For super diffusive, this square root vanishes because gamma squared goes to 2. So a little bit about asymptotic forms. So as I showed on the plot of gamma, for super diffusive case, gamma raises to square root of 2, for subdiffusive case, it goes down to 1. And so it is interesting to look actually what forms of PDFs, asymptotic, okay, what forms of PDFs we are expecting in this, how this gamma, how this Bessel function distribution simplifies. So this is exact result for the moment generating function or characteristic function here. And when you see that if gamma squared goes to 2, this term should vanish. And what you get here, it is gamma distribution. In case when gamma goes to 1, it is even simpler because this thing becomes a full square. And this is simple exponential distribution. Okay. Maybe you told me that for 5 minutes. Okay. Let us look on this last case. Yeah, when you have a simple exponential distribution, and you see that S enters in combination S over mu. And so this is dimensionless property, and all regular frequency dependence of S is hidden here in the first moment. But now the question, in other words, you may say that this ratio is equal in distribution to some rational number B. And it's unclear if you fix, for instance, a frequency and then change it, will it be the same B? In other words, B is not a regular function of the frequency, definitely, but is it a noise in the frequency domain? And what we actually, and if it is, we can have three possibilities. First, it is delta correlated noise. Not like white noise in the sense that it is only positive definite random variable. It can be correlated noise, so something like pink noise, or it can be just a rational number which is independent of noise. And I proceed to show you on 4 examples that actually all 3 scenarios are possible, depending on the precise definition of the process and its range. So to this end, we look on the correlation function BF1, BF2, which is defined like a mean value of single trajectory spectral density of a single trajectory evaluated at frequency F1, evaluated at frequency F2, and normalized by first moment. Or the Pearson correlation coefficient of 2 random variables defined as usual. And of course, these 2 things are linked to each other via the relation. The relation function is 1 plus gamma at frequency F1, gamma at frequency F2, and this is Pearson correlation coefficient. And so if this Pearson correlation coefficient is equal to 0, so they are decorrelated, we should get 1. And all departures from 1 correspond to the correlations between. So we considered 4 processes. First was Ornstein-Uhlenbeck process, for which you get 1 and 1 for unequal frequencies. A little bit more general Brownian generator model, when you have 2 Ornstein-Uhlenbeck processes which are linearly coupled to each other via some coupling parameter U. And with noises, identical uncorrelated noises, we have 2 different temperatures. And it is a very funny system, because if you look on xt and yt as position of a particle on 2-dimensional plane, you realize that when temperatures are unequal, this thing starts to gyrate around the origin spontaneously. So average torque is non-zero, angular momentum is non-zero, and average angular velocity is not zero. And even more complex thing, because also you have a non-zero probability current, and this probability current has a non-zero curve, which means that a part of moving like this, it's also spinning around itself. But you do the same calculation for Brownian generator, and you get exactly the same behavior like for Ornstein-Uhlenbeck. You do for Brownian motion, and now you see that the situation is completely different. You no longer have 1. And if you look on the Pearson correlation coefficient, that you have 40% of correlations for 2 unequal frequencies and both bigger than 0, and even higher if one of the frequencies is equal to 0. Subdiffused fractional Brownian motion, surprisingly, you have exactly the same behavior as for Ornstein-Uhlenbeck process. And eventually super-diffusive fractional Brownian motion, completely different set of numbers here. And also the Pearson correlation coefficient is exactly equal to 1 if both frequencies are unequal and both are bounded away from 0. So BF is a completely correlated process. It is just a random number, which is...
Is it normal that all these correlations are positive, and there is no negative correlation?
No, Nick, but by definition, it is you have 2 positive definitive random variables. And so just summarizing all the result, you see that such a behavior of function BF can be also used as a criterion of what you are observing, anomalous diffusion or not. So these are 3 cases of subdiffusive motion. You have a bounded process, which is Ornstein-Uhlenbeck. You have a bounded process, which is a Brownian generator, and you have subdiffusive FBM. If you have a trajectory or set of trajectories, you do this trick of calculating frequency correlation, you get for all 3 cases of subdiffusive motion 1. For Brownian motion, it's no longer so. And if superdiffusive FBM stays apart. So you can distinguish what kind of data you're doing this kind of analysis, you can distinguish very well what kind of, if it is indeed an anomalous diffusion or not, you are dealing with. So, conclusions, I think, are more or less evident. And let me just thank you for your attention and acknowledge my co-author, so Ralph Metzer, with whom we published lots of papers on FBM and the related analysis. And about two theorems and frequency correlations are my colleagues Alessio Squarcini from Innsbruck and Marinari from La Sapienza, Luca Filizzi, Santa Marinella Research Institute, and Lamberto Randoni from Politecnico di Torino. Thank you very much.
So we have a few minutes more for questions. So if you have any questions.
Yeah, I'm curious if any of these results are carrying over to discretization of that around emotional
Yes, definitely. I'm sure that no, there is a problem of discretization because from doing discretization, you get periodicity. Instead of power spectral density, you have what's called periodograms. And then the analysis is actually to extract from some parts of this periodogram the behavior which are specific to continuous time limit. But in general, discrete cases are much more cumbersome. And we have a special paper with Ralph, actually our first paper on spectral densities, where we did with discrete time random walk, and where we have shown how to tackle it and how to look on some reliability intervals, what to do, what to expect, because there are plenty of interesting things there. But in principle, I think that these two types of theorem, they will still hold for discrete time, discrete space systems. But effort needed to show it will be much more substantial.
There's another question.
Yes, you mentioned briefly that finally you apply this to trajectories.
Yeah.
So can you briefly mention, so then you were able to classify the trajectories, extract these H exponents?
Yes, this was our goal, actually, to extract from spectrum H exponent, yeah. Our initial goal.
So is that on single trajectory or many trajectories?
Many trajectories. But it appeared that you don't need too many, actually. Say, experiments of Matthias Weiss with telomeres in mammalian cells, which is subdiffusive type of FBM with H equal to 1/4, it's well known. And so we got this 1/4 already from 20 trajectories. Now, you see, because in contrast to mean square displacement, which is a single time property, yeah, spectral density average the whole combination of times along the whole trajectory. So in some sense, it is something more robust. And it fluctuates, of course, less.
Can we compute this for Fourier process driven by fraction of ground motion?
Sorry?
We take a Fourier process, but it is driven by a fraction.
Oh, yes, of course. It holds. Yeah, because it will be Gaussian process. You have just to calculate first. No. The only thing which is necessary for the distribute probability density function, it is Gaussianity of the process. But precise form of it, you need to know mu and gamma.
But you think it's going to be different than what we showed in the Fourier table?
No, we know with Ralph and actually in Dennis, we are finishing for about 1 year a paper on mu for Ornstein-Uhlenbeck process with fractional Brownian noise, whatever H is. So we know it. It's not a big thing to calculate.
Any more questions? If not, let's thank Gleb again for this talk.
No, go ahead.